In this video, we're going to talk about Bernoulli's principle, and we're going to start out by looking at a pretty simple situation where we've got a, syringe, and I'm going to push on the plunger of the syringe, and what's going to happen when I do that, oh, well, I made a little mess there, but what's going to happen when I do that is, let's see if I can screenshot this. When I'm pushing, there is a net force on the right-hand side, and therefore there's a pressure difference. There's more pressure on the right than there is on the left. There's no applied force over here. There is atmospheric pressure, but again, there's no applied force like there is on the left side. So when I look at my diagram here, I'm pointing in the opposite direction, but let's suppose that I've got my force here, and there's no force, no external force on the right. So what is this pressure difference going to do? The pressure difference is going to push fluid through the syringe. And what happens to the fluid is, because of the pressure difference, the fluid speeds up. So again, we've got a pressure difference that would be equal to the force over the area on the left here. There's no external force, so we've got a delta P, or a change in pressure from the left to the right, and again, it's going to cause that fluid to speed up. I would notice that the volume of liquid, V1 and V2, are the same. This is not velocity, this is volume. Volume is conserved. And in our last lesson, we talked about how volume is equal to the cross-sectional area times the speed, the velocity. Here, I'll make these volumes capital. And this is called the continuity equation. And our next lesson is all about the continuity equation and how to use it to solve problems. But we want to be aware of it when we talk about Bernoulli's principle, which we are looking at today. So again, the fluid speeds up. When the fluid speeds up, the fluid speeds up because of a drop in pressure. So again, on the left-hand side where we have this applied force, we're going to call that our high pressure, certainly higher on the left. And we're going to call the right-hand side, which is just open, we're going to call that our low pressure. And again, because of this pressure differential, the fluid speeds up. Now, often what we will see then is we'll start to associate and see some patterns. So when we have slower or lower speed, we're going to have higher pressure. And when we have faster speed, we have lower pressure. Just to summarize what we're seeing in this diagram. Again, the speeds are indicated here by the length of these arrows. So this V1 is a bit shorter than this V2. Okay, so let's look at another consequence of that. Another consequence of that is something called lift. So here's a video of me with a piece of paper. I'm blowing over the top of the piece of the paper. I want you to notice how the end of the paper lifts up. That's because of the airspeed. The airspeed above the paper, let me try that again. Oopsie. So what happens is if I'm blowing across the paper, I need to make this a little fatter, don't I? If I've got airspeed across the top of the paper and the velocity underneath is 0, then what happens is we have a lower pressure associated with the space above the paper that has airspeed, and we have a higher pressure where the airspeed is lower. And what happens when we have higher pressure below and lower pressure above the paper? What happens is the paper lifts. This is called lift. So again, this pressure differential causes lift. And the direction of the lift, or the direction of the force, always goes from high to low. Again, the direction of the force always goes from high to low. Okay, let's go back. Oops, done. Let's go back. Okay, so now let's try to put this all together. And let's think about conservation of energy. So what I'm introducing to you here is something called Bernoulli's equation. And Daniel Bernoulli, the discoverer of the equation, actually didn't explain why there was a pressure difference. But Bernoulli's equation was based on observational data, and it is a statement of conservation of energy. And so what we have here are three kinds of energy. We've got pressure, we've got kinetic energy per unit volume, and we've got potential energy per unit volume. You may notice, you may recall that kinetic energy looked like 1/2 mv squared, which is what this 1/2 rho v squared looks like. And then gravitational potential energy looked like mgh. And now we're looking at potential energy per unit volume, which is rho gh. So you can see how those correspond. And what we know is that energy must be conserved. So the total energy at one spot must equal the total energy at another. So, actually, let me change colors yet again. So if I pick a spot here, and I call this point number 1, this purple point, then the pressure, the external pressure at that point, which in my example, it could be atmospheric pressure, and it also could be an applied pressure. Any applied pressure, so like me pushing a plunger. So that pressure plus 1/2 rho v squared at that point. So this is the velocity at that point, plus rho gh. Because energy is conserved, that has to equal the sum of the quantities at the second point. So again, the pressure, and that pressure would be atmospheric pressure plus any applied pressure, plus 1/2 rho, the density of the fluid is not changing, rho v squared plus rho gh2. So we can use this to solve all kinds of questions. And let's try an example. Let's try an example right now. Let's do one with a change in height. So let's suppose I've got a pipe, and the pipe has a radius of 2 centimeters, And this is actually kind of a plumbing thing in your house. The plumbing, if you have more than one floor, it's going upstairs and downstairs. Let's say the radius is still 2 centimeters. But let's say that the height changed. So let's say that, trying to draw a better dotted line. Let's call the bottom height 0. Let's say the top height, let's say the water rises 3 meters. That's about a story, maybe a little less. And what's going to happen when the water rises? It should slow down, okay? And it should slow down because of conservation of energy. Just like when you throw a ball in the air, on the way up, it slows down because of conservation of energy. Now, in this situation, what we're going to assume is that the pipe does not have an external force on it. So the pressure over here is equal to the external pressure over here. We're going to say that P1 equals P2. In other words, there's no plunger. Maybe it's atmospheric pressure, but these two things, P1 and P2, are the same. And so when I ultimately solve this, I'm going to be able to cancel them out. Oh, finally, let's say that the water on the first floor of the house is flowing at 5 meters per second. And our goal is to find the speed of the water up here. And again, we would expect it to be slower. So using Bernoulli's principle, which again is a statement of conservation of energy, I would say that P1 equals, We're also going to say, by the way, that this is water. So for water, our density is 1,000 kilograms per meter cubed. Okay, so I'm going to write out my formula again, just for good practice. Now, I said that P1 equals P2. That means I could subtract them from both sides of the equation in this situation. And now I'm going to plug in some values. So 1/2 times the density of water times the speed of the water plus rho GH, so that's 1,000 times 9.81. Now the height, I'm calling this bottom height 0. Remember, you can choose your own reference frame in physics. And then on the right-hand side, that's going to equal 1/2 times 1,000 times the second velocity, that's what I'm looking for, plus 1,000 times 9.81 times the height. And the height, this change in height, looks like it's 3 meters. Okay, now I'm going to get out my trusty calculator. If I can find one that works. Let's see. This one doesn't work. That's fun. Okay, this is 12,500. Notice that the gravitational potential energy portion is 0. And then over here we've got 500 V2 squared plus, let's see what we get here. $29,430. So I'm actually getting a result that's impossible here, because look what's going to happen. If I try to subtract 29,430 from both sides, I'm going to get a negative number here. And can I set a negative equal to a square and solve it? No, I can't. So actually in this example, there's not enough there's not enough speed and pressure for the water to rise that high. It won't rise that high. There's just not enough speed and pressure. So I'm stuck. The water would actually kind of just kind of rise halfway up the tube and stop. And if that were my plumbing, that would be a big, big problem. Okay, I'd like to go over one other type of problem. Let's do the problem where I had the piece of paper and I was kind of blowing over the top of the piece of paper. And let's say that the velocity, let's say that I was blowing air at a speed of 10 meters per second. Let's look at what kind of pressure difference that would cause. So first of all, the airspeed underneath, let's assume that the air underneath the paper is not moving at all. And again, what we want to find is what is the pressure difference? And then what's the force? Okay, now a piece of paper is really thin. So the height difference here is going to be 0. So when I look at Bernoulli's formula, again, just writing it for practice, encourage you to follow along. When I write Bernoulli's formula, what I'm going to see is that the atmospheric pressure is essentially the same above and below the paper, and the pressure due to height is also essentially the same above and below the paper because the paper is really, really thin. So the change in pressure is really just going to be due to this speed. In fact, if I wanted to find the change in pressure, if I solve this for P2 minus P1, it's going to be 1/2 rho V1 squared plus, minus. So be careful with your algebra and think about this for a minute. I had to subtract P1 from both sides. Oh my goodness, except I wrote it wrong. I had to subtract P1 from both sides. And then to solve for that, I had to subtract P2 or V2, the term with V2 from both sides. So notice that this 2 and 1 are reversed when I do that. Okay, so I'm going to get the change in pressure due to this pressure difference. And we're going to say this is V1 and this is V2. So I have 0 minus 1/2. Now, the density of air is 1.29 kilograms per meter cubed. I want you to imagine a cubic meter, like a meter stick, a cube that's a meter stick on a side. That weighs 1.29 kilograms. It's like how much, the same as a book. It's kind of a lot. Like air weighs more than we kind of think about. Anyway, air is 1.29. And we said, let's assume the velocity of the air is 10. So the change in pressure from 1 to 2, or from below to above, is 100, It's a pressure change of negative 64.5 pascals. Okay, that's pretty cool. And it should be a negative pressure difference because, again, we should have lower pressure above the paper and higher pressure below the paper. So there should be a negative pressure difference from above to below. Now we're going to find the force. We know that the force is equal to pressure times area. The pressure is 64.5 pascals. And now I need the area of a sheet of paper. I'm going to cheat a little bit. I'm going to Google it. The area of a sheet of paper is 93 square inches. Let's see, it says it's 0.062 square meters. By the way, when I have questions, I Google them. Google is the best thing ever. I encourage you to do the same. So the force is about 4 newtons. So there's about 4 newtons of force on that paper, making it lift. All right, there are your notes for Bernoulli's equation. Again, it's a statement of conservation of energy. You want to pick your 2 places in the fluid. Pick your 2 places. Here I was picking 2 places. Here I was picking 2 places, and then apply Bernoulli's principle to solve.